Hello geometers, this is Miss Backfish and I'm here to talk to you about, as you can see, special parallelograms and a couple of other quadrilaterals that we like to talk about when we're talking about all the properties of parallelograms. And what we're going to do first with that is we're going to fill in a chart that is basically a flow chart, not first, but really what we're doing ultimately in this video is filling in a flow chart that talks about how different parallelograms and other quadrilaterals are related. But first thing I want to do is go ahead and just look at these individually and work on think about what their properties are one by one. And we're going to start with parallelograms. Parallelograms have 5 main properties that we look at, and we've talked about these 5 main properties. The definition, opposite sides are parallel. Another property is that opposite sides, and this is both pairs. When we're saying opposite sides, we mean both pairs of opposite sides. They're congruent. Opposite angles are always congruent. The diagonals bisect each other. And consecutive angles are supplementary. All right, so there are our 5 properties of parallelograms, and these are ones we've already talked about. But we're going to keep coming back to these because every parallelogram has these 5 properties, so it's important to remember that those are all there. So let's look at our special parallelograms. Special parallelograms means the 3 shapes we're about to talk about next, rectangles, rhombi, and squares, those 3 shapes are all parallelograms. So what that means is all 5 of those things are still true about these 3 shapes because they are also parallelograms. So we have the 5 properties: opposite sides are parallel, opposite sides are congruent, opposite angles are congruent, diagonals bisect each other, and consecutive angles are supplementary. And then 1, 2, 3, 4, 5, we're going to add some extra properties. So that's why we start on number 6. For a rectangle, we say, okay, in addition to the 5 properties that every parallelogram has, some other properties we have, and I wanted to make the font bigger here, so I'm sorry that I'm not succeeding in that, but we have 4 right angles. Okay, so yeah, look at the tiny little right. But as long as you can read it, it's good, right? Every rectangle has 4 right angles. That's really kind of the defining characteristic, meaning the definition. So anything that has 4 right angles is a rectangle. So that means a square is a rectangle. Everything that has 4 right angles, every quadrilateral that has 4 right angles is a rectangle. The other thing that's true about every rectangle is that diagonals are congruent. Now remember, we already said they bisect each other. Now we're also saying they're congruent. The bisect each other part, that's step 4 here, that says that the diagonals cut each other into 2 congruent pieces each. Saying that they are congruent, that means the whole diagonals are congruent, really means that when they cut each other into 2 congruent pieces each, we really have 4 little congruent pieces. So all the little pieces formed when the diagonals touch each other, when they intersect each other, all 4 of those little pieces are congruent. All right, another special parallelogram that we have, and again, it starts with those 5 properties. So opposite sides are parallel, congruent, opposite angles are congruent, diagonals bisect each other, consecutive angles are supplementary. And then on top of that, for a rhombus, step 6, all 4 sides are congruent. Okay, all 4 sides are congruent. That is the defining characteristic for a rhombus, meaning if that is true, it's a rhombus, okay? Every rhombus has 4 congruent sides, and every quadrilateral that has 4 congruent sides is a rhombus, which again means a square is a rhombus. Another thing that is true for every rhombus is that the diagonals are perpendicular, which means that where they meet in the middle of the shape, they form right angles, okay? And the diagonals bisect, this is a sort of special property, the diagonals bisect what we call the vertex angles, which means that where the diagonals come into the corners, okay, where the diagonals hit the corners of the rhombus, and you'll notice this big shape is a rhombus, so like if I had a diagonal coming into the corner here, it would cut that corner into 2 congruent smaller angles. That's what bisects the vertex angles means, because a vertex is basically a corner of our shape. So if I have a diagonal over here coming into this corner, it's going to cut that big angle into two smaller angles. All right, a square is another special special parallelogram. So those are our three special parallelograms. Let's go ahead and put those here. We have rectangles. Let's see if I can type. Oh, I can type, but it's in black. Rectangles, rhombi. I'm going to do a singular, and squares. Can you see it? Let's see if there we go. Now we can see it. All right. So what's special about a square? Well, a square is a rectangle. A square also is a rhombus. Why? Because it's a rectangle because it has 4 right angles. It's a rhombus because it has 4 congruent sides. So what that means is for a square, all of this is true. These are true. These are true. Any of these properties for any parallelograms, including the special rectangle and rhombus parallelograms, those are all true for squares. Squares have all these properties. Okay, now we're going to talk about our 2 additional quadrilaterals that we talk about when we talk about parallelograms. And neither one of these is a parallelogram, but they are very interesting or significant quadrilaterals. So we want to talk about those. One is a trapezoid. A trapezoid has 1 pair of parallel sides instead of 2 like a parallelogram. So 1 pair of parallel sides is the defining feature of a trapezoid. A lot of times we say exactly 1 pair of parallel sides, meaning only 1 pair of parallel sides is what makes a trapezoid a trapezoid. Believe it or not, there's actually some debate about that in the world of geometry instruction right now. There are some places, some people, some curriculum folks that want to say that a trapezoid, that anything that has 1 pair of parallel sides at least is a trapezoid. So that would make a parallelogram a trapezoid. I'm going with the original, the much longer standing definition, which is the exactly. If it has exactly 1 pair of parallel sides, meaning the other pair is not parallel. Okay, we're going to stick with that one for now. Who knows who will win that debate in the long run. Now, there is also a special type of trapezoid. If you notice, if you look at this trapezoid, when we have a trapezoid, we have 2 things called bases. Let's see if I can. What can I draw? Can I do it? I don't know. I've never used this particular tool. Freehand draw. Sure, I can do freehand. All right, there we go. Okay, this is a base of my trapezoid, and this is a base. Whoa, sorry, this side down here is a base of my trapezoid. The 2 bases of the trapezoid, it doesn't mean top and bottom. It means the 2 parallel sides. So the 2 sides of the trapezoid that are parallel, those are the bases. The other 2 are called the legs, the 2 that are not parallel. So in this case, I'm going to make those yellow. So the legs here are yellow. They are not parallel to each other. The bases are the ones that I just made red. They are parallel to each other. Now, there is a special type of trapezoid called an isosceles trapezoid, where the legs are actually, hang on. I'm having trouble getting rid of my draw and zoom. Okay, I figured it out. All right, so the special trapezoid is an isosceles trapezoid. Just like an isosceles triangle, an isosceles trapezoid has congruent legs. So again, remember I made the legs yellow. This is a leg over here. This is a leg over here. They're the legs because they're not parallel. In an isosceles trapezoid, those 2 would be the same length. They are congruent. Okay, so let's turn that off and see if we can type right here. So legs are congruent. Congruent. There we go. The diagonals of an isosceles trapezoid only, not every trapezoid, just an isosceles trapezoid, are also congruent. Okay, now just like isosceles triangles, isosceles trapezoids have base angles. So let's look at those. The base angles here would be these 2 up here. In other words, the 2 angles on either side of one of the bases. This is a base up here, and there's another base down here at the bottom. So these 2, those are base angles. Not the best drawings, but These two at the top, they are congruent to each other. And the two there at the bottom, they're congruent to each other. It's not really a bottom and top thing. It's basically the two angles on either end of the base would be congruent. So base angles are congruent. And this is the only thing I really don't like about this flowchart is I don't like this phrase at all. Uncommon base angles, that's really an awkward way of saying what they're trying to say. They're trying to say the two angles that are not at the same base. So they're talking about like this one up here, and let's go with, oh, come on, you could do it. This one down here. They're calling that uncommon base angles. We have another name for that, so why would we want to call it something weird? Those are consecutive interior angles. Remember, whenever you have parallel lines, same side interior angles or consecutive interior angles are what? Supplementary. And this is actually something that's true for not just isosceles trapezoids. It's also true for all trapezoids, because if I have two parallel lines, then I have same side interior angles. Let's look here. Here that would be these two, the one down here and the one up here. Those two would have to add up to 180 because they're same side interior angles or consecutive interior angles. And then the same goes over here. This angle right here and this angle right here, those would have to add up to 180 because they are also same side interior angles or consecutive interior angles. So what we can do now is we can put that all together into our big flow chart, and here's what it looks like. Nope, have to turn off the drawing, sorry. There we go. Okay, here's what we have. This is everything that we have said about all these things. Typed a little awkwardly, sorry. And then what I want you to see is this whole, let's talk about this whole sometimes and the whole always. Okay, here's what the idea is behind that. Very often you will be asked to evaluate statements about how these things relate. Like for instance, a rhombus is a parallelogram. Is that sometimes true? Is that always true? Is that never true? A rhombus is a parallelogram. Well, because a rhombus is down here. If I'm talking about this is a this, if I'm going up, a rhombus is a parallelogram always. It's underneath a parallelogram, so it's under the umbrella. It's a member of that family. A rhombus is always a parallelogram. So if I start with rhombus and say this is blank that, always, sometimes, never. If I'm going upward, it's always. A square is, let's do this with some color. A square is always a rectangle because I go up to go from square to rectangle. A rhombus is always a parallelogram. I'm going up. A kite is always a quadrilateral, and I just saw that I did not fill in that top little line. What goes here is the definition of quadrilateral, which is 4 sides. It's a 4-sided polygon, a polygon with 4 sides or 4 segments. Okay? An isosceles trapezoid is always a trapezoid because to speak about those two, I have to go from isosceles trapezoid upward. That's what this always is, upward. Isosceles trapezoid is always a trapezoid. A trapezoid is always a quadrilateral, and so on. Okay, so now sometimes up here at the top, and I'm sorry this little thing is in front of it, but sometimes would be going down. If I say a quadrilateral is sometimes a kite, that is accurate. Or a parallelogram is sometimes a rectangle. Or a rectangle is sometimes a square. A trapezoid is sometimes an isosceles trapezoid. Another way we can think of that is you could say some quadrilaterals are kites. Some parallelograms are rectangles. Some rectangles are squares. Some trapezoids are isosceles trapezoids. Some parallelograms are rhombuses, stuff like that. And technically, by the way, I meant to mention that the technical plural of rhombus is rhombi, R-H-O-M-B-I, but sometimes I'll say rhombuses because I am just in the habit of saying that so that people know what I'm talking about. But you know. All right, so the last thing to look at here is what it says down in the corner, which is the answer is blank if they do not connect. That would be never or no. In other words, no kites are isosceles trapezoids. Okay? These two don't connect. So no kites are isosceles trapezoids. No isosceles trapezoids are kites. Or I could say a kite is never an isosceles trapezoid, or an isosceles trapezoid is never a kite. Or a rhombus is never a kite. Or a rectangle, well, a rectangle can be a rhombus if it's a square, so that one's a little bit confusing. But in general, if there's not a line that goes between them, and you could say that there is a line between these, they could go, they're connected that way. But then there's not a relationship. Now, doing all of this has made me realize I skipped one, and I'm so glad I realized it. We didn't talk about kites independently, so let's talk about those now. It says a consecutive sides are congruent, diagonals are perpendicular, and one set of opposite angles are congruent. So let's talk about what a kite is. Okay, I have used my very favorite geometry software, which is Geometry Sketchpad, to create a kite here. And let's talk about what makes it a kite. Okay, it has two pairs of congruent sides, but they're not, unlike every parallelogram, they're not opposite sides. Those two sides are not congruent. No, it's two that are next to each other. Those two sides are congruent. Let's go ahead and measure those lengths. And look, they are congruent. Ta-da! Okay, and we don't need to really label those lines that way. Let's do it a different way. I want to label them with segment names. Let me pause and redo it. Okay, I'm going to measure AB, segment AB. And then I'm going to measure a segment BC. And ta-da, they are exactly the same. Let's go ahead and measure the other two, these two segments, this one and this one. They should also be congruent if it's really a kite. Okay, and I happen to know because of the way I constructed it that it has to be a kite. So we'll talk about that in just a second. There's AD. I'm not sure why that's calling that B prime. That's a little disconcerting. And then DC. There we go, exactly the same. Now, because I made this in such a way that I'm positive it's going to stay a kite, I can move these things, and you can see they're always going to be the same. So that's still a kite, even though it doesn't really look like one you would fly. Let me see if I can hide that label. Nope, I cannot. Okay, so kites have two pairs of consecutive, meaning next to each other, congruent sides. So those two sides are congruent, and these two sides are congruent. All right, and again, the way I made it, that's always going to be true. And you notice, still a kite, because two over here are congruent, and those two over there are congruent. Now let's look at some of the other properties. One of the other things we said was that in a kite, our diagonals were perpendicular, just like in a rhombus. Okay, so construct a segment, and let's check these two out. I need to get the point where they intersect, and then I'm going to measure that angle. Measure angle. Ta-da! 90 degrees. So diagonal AC and diagonal B, D, or E. This point actually has two names, sorry. They meet at a right angle. Really, all four of those angles are right. Okay, so that's another thing, is the diagonals of a kite are perpendicular. And notice they always are. And it doesn't have to be side to side like this. It could be, whoa, not what I intended, but it could be something a little more vertical. Let's see if I can do that. Nope, it's not working. Okay, another property of kites is that they have one pair of angles directly across from each other. That would be the angle up here at A, the big angle, and the angle down here at C. Those two angles are congruent. Okay, so let's check that out. Angle B, A, D, or E. I'm going to measure that angle. And then I'm going to measure angle the angle at C, B or ECB. Ta-da, those are exactly the same. So these two angles, let's see if I can, this angle here and this angle here, those are congruent. Okay, here's how you can see that, is how I constructed it in such a way to make a kite, is what I did is look at, I'm going to see if I can hide one of these. Okay, we'll just call it B prime for right now. And we'll call that D. Okay, look at triangle A, B prime, D. Reflect it across this line in the middle, and you have triangle C, B prime, D. That's what I did. These two big triangles, and by big triangles, what I mean is, let's see if I can change colors here. Can I change colors? I don't think I can change colors. But this whole big triangle, why are we not drawing? There we go. This whole big triangle and this whole big triangle down here. Oh my goodness, I'm doing some kind of crazy thing. And the phone's ringing. All right, come on, cooperate. There we go. This triangle down here. Those two are congruent triangles. Okay? You could say they're congruent by side, side, side. Because remember, two congruent sides right here, two congruent sides right here, and then the third side is a shared side. So these two angles are always going to be congruent. The other two are not going to be congruent. And remember that in every quadrilateral, all four angles add up to 360. Okay, and one way that we can see that, just quick thought there, if I have a quadrilateral, it doesn't matter what type of quadrilateral it is. If I draw one diagonal, meaning connect one pair of sides, pair of vertices that's not already connected, then I've divided it into two triangles. And every triangle, let's see if I can write 180 degrees here. Woo, it's not the best handwriting, but we can read it. And 180 degrees here. What's 180 plus 180? 360. So every quadrilateral has a total of 360 degrees if you were to put all the interior angles together. Okay, so keep that in mind. All right, and that takes us to the conclusion of our little chart here. And I hope that has helped you to figure out all these relationships between special parallelograms and regular parallelograms and the other two quadrilaterals. Thank you for watching.